physics. We have a big problem with our Zoom. Okay. Our center is at Chiang Mai University because Chiang Mai University is the leading university. Our center have six how to call six university like lead university with 15 network university together when we set up our center and more than 40 laboratories together in our center. And for this activity today is under Hub of Talent for Particle Accelerator. Thailand Center of Excellence in Physics act as the consortium to organize this center. Okay, our center for this particular particle accelerator, we have Professor Dr. Sakon Lim as the lead of the Hub of Talent. Yeah, together with me in this Hub of Talent for Particle Accelerator. Not only for Chiang Mai University, Professor Sakon worked closely with the SLRI, the Synchrotron facility in Kolat, and also other facility like SUT, Suratnali University of Technology, yeah, and also NECTEC and NALIT, yeah. There are many institutes, yeah, that I did not mention. Now we work together, try to make this Hub of Talent to be the center for particle accelerator that closely to academic and also the research facility in Thailand. Not only for the domestic part, yeah, many researchers in this Hub of Talent also connect with international collaboration. And for today also, we have Professor Kuriki with us to share about the title. I don't remember, and I think, sorry, but it should be the issue about the particle accelerator. Yeah, please welcome Professor Kuriki, yeah, for this public talk. Thank you.
Okay, so let me start my presentation. The title is Particle Accelerator for Science, Industry, and Medical. This is kind of the parasite event of the SP24, which is currently ongoing in this campus. Okay, at first, let me introduce. My name is Masaru Fuiki, and born originally in Tokyo, Japan in 1968. Currently, I'm 56 years old, and I got a PhD physics in 1996 from Tohoku University, Japan. And the subject was the heat tackling of porous ethanol, porous butylol, at the Stanford Linear Accelerator Center experiment 143. And after that, I moved to I got the postdoc position at the University of Tokyo, and I worked on the charge of K-plus DLT on decay search at Brookhaven. And after that, I moved to the KK, and I joined the IFC accelerator development from that point. And since 2007 to the present, I moved to the Hiroshima University, and I worked on the electron accelerator and ethics applications. And from the 2023 and the present, I'm the president of the Power of Particle Accelerators Japan. And my study field is currently electron accelerators, electron guns, the particle generation, the nucleators, etc. And let me add one line here that since from the 2001 to 2002, I participated in the Stanford factory as commissioning at that period. So that's my good experience. Okay, let me briefly introduce the ISBA 24, which is currently in this campus. This is the seventh school. The subject is the beam dynamics and accelerator technology, and to promote accelerator studies by giving opportunity to their students and young researchers studying the foundation of the accelerator. That is the motivation. And it was initiated in 2018 in Hiroshima, and as a collaborative effort among the Asian countries. In the Thailand, joined from the sixth school and the past 1 year ago at 4 years. And this is the second ISBA in outside of Japan. This one. Okay, I really enjoyed the life in Chiang Mai. Like this, I became the friend to the elephant. And also I enjoyed the good feeling by learning that the very beautiful stadium. And also I ran up to the hill together with those bicycle. And finally I've enjoyed the good view from the viewpoint. I really enjoy the school and the life in this campus. Very beautiful. Okay, let me move to my the subject. Okay, the first let me little bit mention about what is accelerator. Okay, accelerator itself is very simple. Just energize the particle by the electric field like that. So particle in the electric field they are accelerated and the energy is increased. That is the principle of the accelerator. And that was invented almost more than 100 years ago. And for the very primitive accelerator is the closed tube. And by using this device, this guy, the J.J. Thomson, discovered the electron in 1897. That was the first limited particle which mankind discovered. The device size is like the several 10 centimeter, and the device is as a bias is about less than 100 kilovolt. And the modern physics and the accelerator is much long. Okay, the latest and the largest accelerator in the world is the LHC accelerator in Seoul, as they played it after the 2000, and this facility discovered the Higgs particle in 2012. The scale is 27 kilometers circumference with energy to 30.6 TeV, which is a number of orders larger than the primitive one. Okay, now the accelerator is used for not only for the fundamental physics, but also the industry and medical. Okay, let me briefly introduce what the subject is the accelerator is used to study one by one. Okay, first let me measure the scientific studies, not only the natural science, but also the humanity. Okay, at first is the modern physics has still many mysteries, and one of them is the Higgs and mass. So all particles are massless in simple vacuum. But once Higgs particle is condensed in the vacuum, object get mass and become harder to move. So without Higgs, so the object is moving so fast. But with the Higgs field, so the object cannot move fast. Have to move. So the definition of the mass is kind of difficulty of movement. So the Higgs is generate mass. And if you feel your body is heavy, do you think so? Okay, you feel the Higgs effect of Higgs. But somebody you don't associate in my body is so light and maybe you are like a fish in water. That means that it is in water, there in water, but it doesn't feel water. Okay, something like that. Still the Higgs is around you. Okay, Higgs is kind of a matter because if there are no Higgs boson in the world, all particles would move around at the speed of light. So they cannot stop without mass. So that means that not just planets or galaxy, but even matter molecules like hydrogen or water would be impossible to exist. So the world doesn't exist without Higgs. So that is very important. And also the another mystery is the stability of the universe. Okay, the left figure shows the vacuum potential determined by the Higgs field. And currently, so we are here, the other ground state, the lowest the state of the vacuum. But depending on the shape of the Higgs, the potential, this could be real ground state, or maybe the true vacuum might be used, for example, like this. The currently we enjoy our universe like this. If you have the holiday, you can enjoy your life. But once might be the ground state transit to the true vacuum. So the ground state will be changed suddenly. So universe to transit to the true vacuum, then the people are falling down to the real ground state. So we can survive in that case. So vacuum, the stability of the universe quite important. Okay, another mystery is the cosmological function of the energy. Okay, currently we know we understand that only 4 or 5% of the universe, and other 95 or 96% is shared by so-called dark energy, the dark matter. Dark matter is observed by observing the rotation of the galaxy, and the dark energy can be considered there is by observing the accelerated expansion of the universe, some unknown energy. Okay, anyway, the universe is ruled by the dark sector, which we don't know at all. So we have to understand what is the dark sector. Okay, in terms of linear collider, this is the electron position collider based on the superconducting linear accelerator. Like this will reveal the mysteries by observing the electron position collision, which will generate the dark matter, many Higgs particle, or can study the vacuum breakdown, and even the extra dimension of the universe. And the candidate side of the RC construction is the boundary of the Iwaten near prefecture in Japan. and we want to build RC soon. Okay, Higgs coupling and mass is a very important subject to be studied by RC. So RC can measure the Higgs coupling, that means the strength of interaction to each particles. So if we plot the coupling as a function of the particle mass, and in the standard model, the Higgs coupling and the particle mass are in proportion because the Higgs mass coupling is genetic mass. So each particle should be on the straight line with a 45 degrees, right? But if there is any deviation from this line, it's a strong evidence there is a new mechanism beyond the standard model. And the deviation pattern depends on the cell weight. So we can evaluate the cell, we can examine which cell weight is more feasible. About the stability of the universe, we can evaluate the stability. So this diagram shows the stability of the universe, and the red area shows the unstable region, and the green one is a stable region, and the yellow area is a metastable region. So current measurement value is in the metastable area, but with large error. So if we study with the LC, can evaluate the vacuum stability with a much higher accuracy, correspond to this red small red circle. So we can examine the vacuum stability, and LC could confirm the stability of the universe or not. Okay, next, let me think about how to detect the dark matter in LC. Because E plus mass might go to the appeal of dark matter, but the dark matter is invisible. So that means we can, as an event is something like E plus E minus goes to nothing. So how we can detect the invisible particle through this the interaction like this. But idea is, so we can detect the dark matter as a missing mass because we know the initial energy of mass, because the initial energy of the electron and positron is well known. So if there is a missing mass from after some event, and this event occurred many times, so this is a strong evidence that there is a dark matter. So we can analyze those events. So we can evaluate the property of dark matter like that. So this is so horizontal axis is the liquid mass, which is kind of the missing mass or missing energy. It's in the Higgs decay. Okay, the last topic in the scientific studies related to the ecology, history, and the cultural property analysis, dealing with the carbon-14. Okay, carbon-14 is a radioisotope of carbon, and it is generated by the cosmic ray interaction and the decay with the more than 5,000 half-life. So there is a balance between the usual carbon and the carbon-14 in environment. But if subject is isolated from the environment, the ratio will be changed as according to this the half-life decay curve. So by measuring the ratio of some object, the age after its death can be estimated according to this the equation. So this idea is very old, but the conventional method to measure the content of carbon-14 is count the beta decay from the carbon-14 like that. But in this case, the number of signals is very small, few, and we need a large amount of material, even though the accuracy is very limited because of the very small amount of signal. Statistics is very poor. But if you use the so-called accelerator mass spectrometer, we can analyze the whole sample. So we can count each carbon-12, carbon-13, and carbon-14. for all sample by ionized. So then we can obtain the many signals, and the small amount of material is enough for analysis, and the statics is very large, so the accuracy is very high. Okay, this is a typical accelerator for the AMS analysis, which is a kind of static accelerator. So carbon ion is extracted from the sample and accelerated up to several MeV and analyzed by the model. And the accuracy is several tens years as the highest with AMS. That is much higher compared to the very big amount. So by using this technology, so there are many progress in various fields that I can show you several examples. For example, the dating of pottery shells reveals that the beginning of the Neolithic period in Japan. It's back to the 16,000 years ago. It used to be we considered only 10,000. But according to this AMS measurement, the history is extended 6,000 years more. And another example, this Egyptian mouse teacher noted the researcher determined it to be not real, maybe he said maybe a new one. But this object is measured with the AMS method and determined to be it really came from the 12th dynasty of Egypt. So that means that this is a true object. And everyone must know the famous Louvre Museum in France. And at the ground floor of this museum, there's there's accelerator, so-called Agulai, which is placed for analyze for the artwork with so-called PIC. So by using with PIC, so analysis can be done without any damage on the artwork. So that this accelerator is still used in this museum. Okay, next we'll move to the industrial applications. Okay, there are many applications in the industry too. So one of them is, for example, by using the accelerator. So by radiating the air or the water as a subject, so we can clean up some toxic the compound like the oxygen, virus, pathogen, sulfur oxide, and PFAS, and even PCB. So that is can be used for the environmental cleanup. So it can lend us to the harmless and safe drinking water, like the medical equipment to remove toxic substances from the environment and more. And also, irradiation of the beam can be utilized to make the close linking and the polymer degradation of the compounds. So if we irradiate the electron beam on the polymer, the many kinds of the interaction, some chemical reaction will be induced. And by using adjust the same as a proper condition, for example, that you can improve the durability and performance of the car tire, or we can develop some functional material like chemical filter, or maybe we can improve the durability of the asphalt paving on the road. Another the application is thermonuclear nuclear reactor by using the proton accelerator. So we use the proton accelerator to make the main neutron by fission product separation reaction. And this neutron cause the nuclear interaction to generate, for example, electricity. This part of the electricity can be used to operate the product accelerator, and rest of them can be used for the public use. And because it is subcritical, so runaway is not covered in the system. And also this system can generate tons of the neutron, so it can be applicable to produce many RI or nuclear waste treatment. That means the long-lived nuclear waste is converted to the short-lived nuclear waste for easy to treat. And recently, the non-destructive inspection by accelerator is important subject because many structure like the bridges or buildings is in age, and maybe the damaged structure will be renewed. But we don't know the real damage inside of the structure. So inspection is very important. So inspection of the large structure, such as bridge and buildings, are important for proper infrastructure renewal. And the conventional method is the acoustic inspection existed, but the resolution is not enough to investigate inside of the exact state and the status of the inside of the structure. Non-destructive inspection using quantum beams by accelerator enables the safe inspection that include the X-ray. This is really in use. And the neutron and neon inspection might be coming eventually. Okay, ion implantation by accelerator is to develop the semiconductor devices. So by implanting the certain ions such as phosphorus or boron into silicon substrate, the structure of the semiconductor is broad. And with nano-sized beams enables the further miniaturization and the performance enhancement of the device. And also it is also characterized by a high degree of process flexibility by, for example, controlling its energy. We can control the depth of the ion implantation. And also let me emphasize that it is an eco-friendly the process than the chemical method because it allows highly pressure stopping and less environmental impact. Because we usually use tons of chemicals to produce this kind of process. Okay, and the next is accelerator is the EUV light source for this blood. So currently the EUV light, the wavelength is 13 nanometer is the latest the technology for the lithography generated from the plasma laser. But the next generation lithography can be there down to the less than 6 or 7 nanometer beyond the EUV light. So in that case, accelerator, so that the FEL-based light source can provide the wavelength like in this wavelength because the wavelength from the FEL is inversely proportional to the square of the energy. So since wavelengths can be shortened simply by increasing the energy, so there is no need to worry about short wavelengths lying in the future. So that is the strong candidate to provide the light source for the lithography future. Okay, let me move to the medical application. Okay, as you know well, the medical and accelerator has a close relation, starting from the discovery of the X-ray by Dr. Röntgen more than 100 years ago. And this is a picture. This picture is a very famous picture of the wife of Dr. Röntgen's hand. And you can recognize the ring here. It looks like very gorgeous. And right after the discovery of X-ray, this technology is applied to the inspection of the human body bone from And after that, this X-ray is used in many cases, some health check or the X-ray CT image, and also by employing the nuclear medicine, we can add some additional information by using for example, PET technology. And also particle beam is directly used to the therapy for the cancer, in case of the particle beams and X-ray beams. Okay, therapeutics of the cancer with accelerator is one of the major application of the accelerator in the medical field. So by shooting the cancer cells with a particle or X-ray beam, the cancer cell can be killed. So then by using the heavier accelerator or the accelerator, we can do the therapeutics for the cancer patient. But by considering the energy growth as a function of the depth in tissue, so the ideal radiation treatment kills only the cancer cell and no damage on the normal cell. That is the ideal which we want. But by considering the dose as a function of the depth in tissue, so okay, the carbon and proton cases, the damage can be also treated on the cancer, but not in the X-ray case. But anyway, both in the proton and X-ray, some other area is also damaged. So that means that this is not ideal. So X-ray irradiation always affects the normal cells, even the damage is limited comparing to the cancer cells. So the question is it possible to shoot only the cancer cells? That is the next issue for the cancer treatment. Okay, the hint is coming from the sci-fi novel and famous from the fantasy voyage by Isaac Asimov. So in this novel, as a tiny submarine and navigates through the banks of the Styx, so destroys below the coast in the blood vessels to the brain and saves the dying sick person. That is the very last story of this novel. This is a very tiny submarine inside of your body. Okay, if you can make this kind of technology, so we can operate this submarine to the cancer cell, we can directly shoot only the cancer cells. That is the idea. The similar thing is possible by employing the nuclear medicine. It corresponds to the tiny submarine in the novel. So radioactive isotopes combined with molecularly targeted drugs that attach only to the cancer cells. So our medicine is administered to the patient, and the drug is delivered to the cancer cell by the targeted drugs. So radiation is produced inside of the cancer cells, and only the cancer cells are killed. So that corresponds to the tiny submarine. Okay, the nuclear treatment is the history is long. The first one is done in the 1941. So almost more than 80 years ago, the US Dr. Sauli. So he administered as iodine 131 to a patient with hyperthyroidism. And this, the newspaper is a report that this patient is recovered with this treatment. And recently, the cancer diagnostics with nuclear medicine is common, so-called PET. So in this case, the almost the same drug delivers a radioactive isotope that produces the gamma rays or boson in case of the PET into the cancer cells. And the gamma rays are generated in the cancer cells. Gamma rays have strong integration power, so they can pass through the outside of the body and detect it at the contact surrounding the body. We can determine the rays of tumor cells by observing the gamma ray from the medicine. So distribution of the cancer cells in the body can be determined by measuring the gamma ray by something that this is one of the PET image. So red press is the hot spot where we strongly suspect the cancer cells. So combining the therapeutics and the diagnostics with the nuclear medicine, so the concept of therapeutics is commonly used nowadays. So in this case, depending on the types of radioisotope delivered, the same drug can be used for diagnostics and treatment. And the repeated diagnostic and the treatment allows objective evaluation of treatment efficacy. And accelerator provide a wide variety of radioisotope for the therapeutics and diagnostics to support this treatment and diagnostics. Okay, this is a famous example of the cure of a terminal cancer. Okay, it's a progress of some patient. So in the A, this is a PET image, and the black area is cancer tumors. So measured by PET, and so this is a serious situation. So the cancer cells widely spread as not only the original breast, but also the whole bodies. And by injecting the lutein, new the medicine twice, but there is no progress. Even the cancer is grown further. Okay, lutein is emitted the beta ray. This range is several millimeter, and the damage is spread thinly over many cells. So the effect is less. So then the medicine switched to the actinium-225, which emits the alpha rays. And this alpha rays range is typically micrometers or 10 micrometers, and the damage is concentrated on a single cell, single cancer cell. So after twice treatment with actinium, so the most of the cancer is disappeared. And further injection of actinium-225, so the cancer is disappeared at all. So this patient is survived. That was very impressive as a case. Okay, the next is the topic is the strategic drug discovery. So traditional drug discovery is a kind like this. So search for medicinal properties among tens of thousands of natural and artificial chemical compounds. So we need a very long time and much effort, and the high development cost is resulted. So it is something like to find the gold vein in a large mine. So it is very hard. It's hard work. In contrast, recently the drug is discovered with some strategic way. For example, if we consider some allergic as a disease, by for example, hay fever or something like that. So disease develops when specific ligand molecules bind to the receptor, something like that, histamine receptor here. So if the histamine is bind to this receptor, the disease is occurred. But if we can develop the blocker, some drug prevents the disease by interrupting the ligand, something like that. The blocker prevents the histamine bind to the receptor. So in this way, the blocker drug is designed somehow. And to design the accelerator, the sync neutron radiation from the accelerator has a very important role. So there's a FEL and also the storage link right source is used for the drug discovery. And in various phases like structure analysis, structure determination of the big protein, or analysis for ligand the compounds, and to investigate the delivery system and to perform some drug screening. So in various in those fields, those phases. So synchrotron right is used. Okay, at last, let me introduce maybe you. Okay, the sign of the source is the first light as a storage light source in Thailand. And I'm proud to join the commissioning of this facility 20 years ago. So currently, it operates 1.2 GB storage link. This provides the simple right for various usage. And you have another the facility, the infrared free laser facility at this campus. So there are two beamline able to generate the different kind of the light. And I introduced the simple storage light source, and every year is very useful for the drug discovery. But Thailand has a both synchronization facility, not only for the light as a storage light source, but also for the field. That is not I can say this is not the usual country. So I believe that the Thailand is among the largest country in the absolute field. Okay, let me summarize my talk. So accelerator is meant to boost up the charge particle energy by electric field. So basically it's very simple. But the accelerated beam can be used for various fields, scientific studies, industrial application, and the medical application. And accelerator drive cutting-edge research in this the respective field, the science, industry, and medical. The research accelerator will lead to the latest research in their respective fields by significantly improving the performance of accelerator. That is also important. So Thailand is a leading country in Southeast Asia for accelerator research, covering the third generation light source and FEL. So we look back at further expansion of the accelerator research in Thailand, and also strongly recognize that Thailand is an important partner in supporting accelerator research in the Asian region. So that is it. Thanks for your attention.
And we have a question in the chat.
Chat.
There are questions in the chat box.
Yeah, can I see?
You can please, I give only one question.
There are two questions.
Yeah, I thought I just blocked it.
Yeah, Professor, you can see from here. There are two questions.
Okay. The one of them is the gap. So for the diagnosis, I say the gamma is used, but what is the advantage to other?
Yeah, Professor, please, the microphone.
Okay, the question is the gamma ray is what is the advantage of gamma ray inspection contrast to MRI or X-ray CD or something like that? So the advantage is of spatial resolution. Okay, the resolution of MRI or X-ray CDs, maybe for example, if we cancer cell more than several centimeters is required to discover, to identify. But in case of the spectral PET technology, several millimeters is enough to identify the cancer cell. The spatial resolution is different. And what is the second one? Okay, radiopharmacy doesn't give any damage on tissue. Yeah, just due to the directly to the body, so there is no damage to the tissue. Okay, that's the strategic drug exhaustion. The and possibly yes to the dopamine. Okay. Okay, so the efficiency is much improved because of typically there is in the traditional way as I said the several tens of the thousand compounds were examined to the effect on some diseases. So it takes a longer time and we the met, for example, many researchers to promote this as an experiment. But in the case of the drug, the strategic design, so we have to perform some structural analysis, but the time and the manpower is much less than the traditional one. So it's of course. Okay, yeah. Maybe I don't understand exactly what they ask, but maybe we have to understand what is the mechanism of some disease, but why the disease is happened. So that is I can say we have to understand at first. Is the answer for your question?
Not sure if you see that. Professor, I have one question.
Okay, go ahead.
So you said that we don't have to worry. We want to go for shorter wavelength by just increasing the beam energy. But in order to increase the beam energy, we also have to make even bigger machines. So yeah, if we may have money, maybe it's not a problem. But if we don't have enough money, what is another alternative way that we can
Maybe
consider?
it's better to ask to Professor Hama as the expert of APL. But what, yeah, well,
Using the energy,
yeah.
your question regarding LPO.
I think for any possible
Okay, so, Professor Porky told that, wavelength is proportional to the inverse rate. Gamma square, then however, the gain, every gain is a solid power. Order of solid power is decreasing. So increasing the beam energy. So we sometimes we get an advantage, but sometimes we get disadvantage. So it's very difficult to choose the energy and the targets and applications depending on what you want. So the energy, so it's the absolute of physics is hasn't done doesn't. Okay, so we have at least some of the limitation at this moment. So the future, we don't know, so we have to open the problem regarding consider business.
Yeah, maybe the short period as the magnet undulator is one of the way.
Yeah,
Yeah,
program.
yeah.
Zach, do you have any more questions? Yeah, if no more questions, please thank the speaker, Professor Philip. Can be Professor Kagunwat from SLRI. So we will switch from Japan side to Thailand side. This is one, SLRI is also one of the biggest facility that we have in Thailand. Okay, please welcome Professor Kagunwat.
Okay, so good afternoon, everybody. My name is Thakon Wat Jalanna. You can call me Thakon Wat, or my nickname is Pop. But some of my international colleagues, I prefer them to call me Taki. It's easier for them to recognize me with my full name. I will give you a little bit of my background. So I was born in Bangkok. I did my undergrad from Mahidol University. And then I got my DPhil or PhD from University of Oxford. My thesis focused on short power radiation. I worked on some part with the simulation of the laser plasma acceleration as well as the low alpha mode from diamond ring as well for the experiments. And then I've joined SRI since February 2017. It's almost 8 years that I'm with this machine. So today I will give you the brief overview of the accelerator projects that right now SRI are working on. So as I said, first of all, I will say something about synchron light sources in Thailand. There are one right now, the next one will come soon, and then we have some of the projects for the linear application as well. And then we also have the group working on the accelerator mass spectrometer as well. So this is a public talk, so I prepare some like basic background if you haven't heard about synchrotron. So synchrotron is actually the machine. Normally it's come in a polygon shape, or you can say sometimes you can see it as a donut shape. We have like the small one. You can see the comparable size of the magnet and this man here. And then we also have the largest one in the world right now. The circumference is about 27 kilometers, as the Professor Kuriki also mentioned about LSC at CERN. The magnet is huge. And then we also have one, this figure taken from some part of machine at SRI. So synchrotron, as I said, actually the particle accelerator, normally the shape like donuts, and then each time particle traveling in each turn, it will increase the energy. There are some of the main components. The first one is the bending of dipole magnets. It's normally used to bend your beam so that it's travel into the closed loop. And the next one, you have the dipole magnet you use to focus the charged particles, which functions similar to the lens for the optics. And then last but not least, you also need the part that will give energy to particles, which is the RF LEDs. And also normally we will take the particle traveling into the vacuum chamber around the machine. If you have the particle moving around here, it will get the energy each time it's traveling past through the RF LEDs. And then in order to keep the particle traveling in the closed loop in the same shape of the machine. So I promise this is the only one equation I put in here. You can see it on the left, we have the product between the magnetic field and the curvature or radius of the bending magnets, which is directly proportional to momentum of the particle. So if the particle move faster and get more momentum, you need to increase the magnetic field as well, so that you can keep the radius constant. And then you need to increase both of them synchronously. So this is one of the main reason that we also call it synchrotron. And they have two nicknames as well. If you use the machine mainly to boost the energy, you can call it booster. And if you use it to keep the energy at specific energy for application, you can call it storage. And there are two main usage of the synchrotron machine. First, we use it as a particle collider for high energy physics. And the other way around, we use the synchrotron to generate radiations, and then we call it synchrotron light source, which I will mainly focus on the light source part. So nowadays, if you go to the Google map and then try to find around search about synchrotron light source, you can try to find synchrotron light source around the world. Right now, there are more than 50 facilities around the world, and I can say that the number of the synchrotron light source is keep growing right now. And then I will tell you something about my institute, Synchrotron Light Research Institute of SRI. Our campus right now is located in Nakhon Ratchasima province in northern east of Thailand. We have three main missions. The first one to do research on the synchrotron utilization as well as the technology related to synchrotron. Secondly, we also provide a synchrotron beam service for other people to use as a user for their research as well. Last but not least, we also promote transfer of knowledge and specific specialize in the synchrotron technologies. So you have heard about synchrotron machine. Right now, I will say something about synchrotron radiations. The synchrotron radiation is actually the electromagnetic wave normally generated or emitted from charged particle, which is travel in the curved path. Normally, is traveling curved path by passing through the bending or dipole magnets. Then the charged particle lose some of its energy in terms of the electromagnetic wave, and then we call it synchrotron radiation as we get it from the synchrotron machine. This is the historical picture here. It's the first time that we can observe synchrotron radiation. It's in the General Electric company in 1947 in US. And then this is the first light that we can record in Thailand, the first synchrotron light back in 2001. As Professor Puriki said, he was here 23 years ago. And then I would say like why we need the synchrotron radiations, why it's very important for research. The first probably is that is the electromagnetic wave with broad and continuous range of wavelength or energy of the radiations. For example, you know infrared, you know UV, you know X-ray. But from synchrotron, we can get all of them, infrared, visible, UV, and X-ray. It depends on which one you want to use. You have to design the beam lines to extract at what region you want to use, and then you can use it for your experiment. And also, its brightness is very high, very, very high, like million times higher than the sunlight. And also, it comes in a pulse structure. So normally, when you do the experiment, you don't need more. The scale that you will use for do some experiment is like sometimes like a few minutes you can finish the measurement. And then to use the synchrotron lights for experiment is actually depends on the interaction between the synchrotron radiation with the matter. The techniques depends on different kind of interactions. If we have the electron photo emission, we can use it in the technique called X-ray photo emission spectroscopy. And we can have diffraction, which used in crystallography. Small scattering, we normally use it in the technique called small or wide X-ray scattering. And also the absorption, the material or the elements in the sample, they absorb X-ray in different wavelengths, so we can know that what the element in the sample in the techniques called X-ray absorption spectroscopy or X-ray does. And also we can use X-ray to do the X-ray imaging as well, like the one that we do in the hospital. But this one, when we use synchrotron light, we use X-ray from synchrotron. We have very high brightness, so we can scan to make X-ray imaging with very high resolution as well. And then we have also fluorescent as well, XRF. And also not only X-ray, X-ray is famous because it's X-ray from the free charge particle, so it's not bind with the energy level of the atom. But we also use infrared as well for the experiment. It's very famous in Thailand for the food and agricultural research because they want to know about the vibration of the functional group or some molecules which normally they interested in the field of research. But then the key to using synchrotron light is to reveal or uncover the hidden information or feature or properties from the materials. If you know more about materials, you can do R&D, you can design new material, you can do lots of applications with the knowledge. So then I will move on to our machine. Its name is the Yang photon source. Previously we call it just the Yang photon source, but right now we have the second one. So right now we call it the Yang photon source 1 or SPS1. This is the layout that you've seen from Professor Kuriki's slide. I give you, this one is the cross section of the building of the machine. It normally has two levels. In the underground, this is the first part of the machine, and then the main part for experiment is on the ground floor. In terms of the parameters of the machine, we have the maximum electron energy of 1.2 gigaelectron volts with a solving current of 150 milliamps. And the circumference of the storage ring for the experiment is about 18 meters. And this is the layout of the machine. I'll give you some real photo from the machine as well. I will talk you to different part of the machine first. We use the electron gun to generate electrons, and then we accelerate in the first stage with the linear accelerator or Linux to about 40, the energy of 40 mega electron volt. And then later on, we put in the booster ring to accelerate to 1.2 giga electron volt. After that, we pass the beam through the synchrotron to the storage ring to keep the beam for beam service for about 11 to 12 hours in each shift. And then the electron, when it's spent from the bending magnet or is easily passed through some of the special components called insertion devices, then we generate the synchron light, and then we get the synchron light extract out through the part called beam lines. And then at the end of the beam line with the experimental station for the experiment in different techniques depends on the beam line that you design. And this is the overview of all the beam lines we have right now. We have 10 beam lines, 13 experimental stations. I will not go into the details, what the beam line, what the techniques. You can go to our website and see the information. And if you want to use the synchron for your research, you can see which one is the best. In terms of the application of the synchron, there are lots of users come for the experiment, and then I just show you the main research field that normally the users come to use, ranging from medical and health research, material science, agriculture and food, environmental research, as well as the famous energy research right now, and also some humanities and cultural heritage research as well as the cosmetic. I will give you some of the example that we have done. So the main one that we provide synchrotron light service. So there are ranging of application. I just show you some example here. So for the medical research, we sometimes we get the information from each technique so that we know about, for example, the structure of the protein in the spike of COVID-19, so that you can design the vaccine to block the COVID-19 not to catch with your cells. Or you can do the X-ray imaging to study the bone tissue as well. And then there are some companies that come to Synchron to develop their product as well. You can find it easily in the department store or convenience store right now. And also lots of food and agricultural projects that come to us, ranging from coffee beans, instant noodles, pork, and rice, and so on. And then the main one, we have research on our side as well. Researchers on our side as well to do research on battery materials. And also we have the group that specialize for the agricultural research as well. And then we also have two main of the utilization of synchron technology as well. The main one is the accelerator research and development technologies. We can apply the knowledge that we have run the machine for more than 20 years. We can stand on our feet and then support our machine. So then we have the skills and readiness to do the new project, for example, the Linux applications, as well as the new machine projects. And then we also have our workshop on site so that we can support for other university and the agency who wants to do some engineering designs or fabrications as well. And this is just to give you some of the examples of the products that have been comes to us and using raw life for their research. But actually, if you see in the database, it's more than this, but then they are not allow us to to talk about because they want to keep the secret. And then we have run, as I said, we have run the machine for the beam service for more than 20 years. But right now, as you back in the slide, you have seen lots of beam lines. It's not just beam line, we need the space for the experimental station as well. So right now, if we want to have the new techniques, we may not have enough space for the new techniques, as well as the beam service time is also limited. So that's why one of the reasons that we start the new project, the open source tool as well, to get the higher quality for user and to get the better machine. So then the SBS2 open source too. So these are four objectives that we got on. First is to build the science technology infrastructure in Thailand for innovation ecosystem, and then we try to transfer the knowledge of the technology to the company, to the Thai industrial sector as well, in order that we can build the company in Thailand to support the machine. And three, we would like to build the new generation of researchers and engineers who work on the certain technologies. And third, we will support the research, for example, the frontier research and new kinds of research that require very high quality synchron light for their research. And this is the overview to compare the sorting of the existing and the new machine. There, I can say like the SBS1, the size of the sorting is about the basketball field, but then the new machine is 4 times larger in terms of the circumference. I can say it's about the football stadium. In terms of the parameters, I compare it here. The energy of the existing machine is 1.2, and then the new one is 3 giga-electron volt, which is very optimized energy of the synchron lights all around the world. And then we target at the installed beam current of 300 milliamps. It's double of the existing one. In terms of the number of the beam lines, the high quality, the beam line based on the insertion device that we get very best of the property of synchron light. At least we will have 22 available for beam lines. And the brightness from the new machine will be higher than the existing one. And then on the bottom here, I'll show you the range of the radiation that we will get compared between the existing and the new machine. So we will reach higher hard X-ray energy from the new machine. But then the location for the new machine is not in Nakhon Ratchasima or Korat anymore. We plan to build a new machine in Rayong province to support the area called Eastern Economic Corridor Innovation, or EECI, which is in the area there are lots of industrial companies that we would like to support them to do the research and to advance their technologies. And this is the render of the layout for the campus here. And then, as I said, the main goal is that we're trying to build and fabricate most of more than 50% of the components domestically in Thailand. So that's why we want to work closely with the company in Thailand. And this is just to give you a brief idea of the timelines. We are right now almost 2025. So we will finish the company approval as well as sign loan agreement. We will use the money from JICA from Japan to build a machine. But then we expect to open for beam service within 2033, about 9 years from now. And this is the layout of the machine as well as the first phase, phase 1 beam lines. So the component is similar to the existing machine starting from electron guns. After that, the LINAC, but then we change to have high energy LINAC to 150 MeV LINAC. And then the booster will be in the comparable size to the storage ring so that we can put it in the same tunnel as the storage ring. And then there are 7 beam lines in the first phase, ranging from different kinds of techniques. So I will not go into the detail right now. And in order to achieve the goal that I said, we want to build most of the component, more than 50%. So we will have to start with the project to do the prototype of some components. And this is the design from the beam dynamics. And then this is the 3D render from the engineering design. So we would like to build the real one to compare with the model that we have. So the main three systems that we focus to build the prototype right now, up to now, is their magnets, vacuum chamber, and also the girder, the support to put the magnet on. Which three of these we need to use a lot, as the ring there are more than 300 meters. I would say more than hundreds of them that we need to use it. And then I can start with the magnets. So as I said, we work closely with the company so that we can fabricate both the core and also the coin, and then we have managed to work for the first half sales with the companies. There are different kinds of techniques. There are different type of magnets in there. We have done the dipole, quadrupole, sextupole, octupole, and also we have one kind of combined function dipole and quadrupole magnet as well in purple here. And then the vacuum chamber as well, we work closely with company. Right now, we managed to finish the chamber for the first half cells. And also the girder system. We've designed in the engineering design, and then we work together with company. Right now, in the three system, we have here this one, the prototype that we put them together, which is the half cells, the first one. And then right now, I don't show you the photo. We also have some prototype of magnet for the booster that's already on our site. And then I'll move on to the other projects that we also have in our institute, which is the Linux applications. So we have the goal to build a system for food irradiation. This is the layout of the machine. So we have the DC gun, then small short Linux, which is a side couple Linux to extract electron to 6 MeV, and then we will put it through the beam lines and then hit the target to generate X-ray for food irradiations. And also we expect to get the dose within 1 kg for range of the applications here. And then I give you some parameters here. If you're interested in, you can see it later. And this is the layout of the design. And there are systems that we focus to develop, ranging from the Linux system, beam transport line irradiation system, as well as the RF system and diagnostic, as well as the control and data acquisition and analysis as well. And this is the photo from our site, the real machine. We have done the commissioning of the system recently. You can see here the light that we get the electron beams, and then we can record with the cameras here, the light shine here. Yeah. And then we also measure the energy as well, and then we also use the X-ray to test to do the imaging. And also, in order to use it for food irradiation, we need to do the database of the irradiation on different kind of food as well. Right now, we've done like 4 or 5 kinds of fruits, and give you some like strawberries, mangosteen, longan, and mango. Okay. From our experiment, we can say that the irradiation from our system can extend the shelf life about 10 days. And then we can reduce the bacterial proportional to about to order of magnitude. And then there is no significant changes in the acidity and the sugar content. And then we keep going with the project so that we can have the machine that can really use for any companies to adopt it to use. And then there are also other groups to work on the accurate mass spectrometers for radiocarbon dating as well. As you heard from Professor Kuriki talk, it's very important that we need to measure carbon proteins in order to date, to know the age of the the dye organisms. And then this is the layout of the design that our group working on. Starting from here, the ion source, and then it will transfer to the bending magnets, and then pass through the tandem accelerator, and then pass through the high energy bending magnets to split the beam with different mass, so that they can detect carbon 14 and carbon 12 to do the ratio and counting to calculate the date of the sample. And then they expect to finish and then on operation within 2026. And then last but not least, I will mention about the future forward. Right now, in Thailand, we actually have the very first proton therapy machine in Bangkok, in Jura hospital here. As Professor Kuriki mentioned, that it's very interesting to use proton to treat the cancer cell, which is deep inside our body. But then this one is based on cyclotrons. If you want to change the energy, you have to degrade the beam, and then it results in the radiation damage as well as the beam property will be dropped down. So if we can change the energy freely, so we can change the depth of the peak dose as well. That's why there are interests. We are some group in Thailand right now. We are interested in to have the synchrotron-based proton therapy center. And this I just give you some of the examples of the machine. So if we have the proton synchrotron, we can change the energy of the proton. Normally, you can change the machine here. For example, they can change the proton energy from 70 to 230 MeV, so that we can scan in depth as well. And then in the near future, we will start the project to build the prototype of the magnets for the proton synchrotron as well. Okay, now I will conclude my talk. So SBS1 is currently operating as the biggest synchronized source in Southeast Asia, not only in Thailand. This really is the best one in Southeast Asia right now, I can say. And then the SBS2 will kickstart the construction soon, and then we plan to operate it by 2033. Linear application is being developed for food and irrigation. We have the next target. We will focus on the cargo inspection as well. And then the AMS project, the group trying to complete the project, and then operation is operated within 2026. And then it's very good opportunity to start the magnet prototype for the proton synchrotron. The last word I would say is very best time for researcher and especially Thai students that really interested in accelerator project. There are lots of projects that you can join. There are another project that Professor Sakon will tell you about as well. I would say again that is very best time for students for the accelerator field in Thailand. If you want some more details, you can go to lots of social media that we have right now. The newest one is the TikTok. I have never went to the TikTok as well. I have no idea what's inside. All right. Okay, then thanks very much for your attention.
Any question?
Yeah, Professor Sakonwat already answered you the job opportunity for accelerator. Okay.
Okay. So you said that you want to develop the industry to provide the accelerator component.
Yes.
For the next coming time of Photon 2.
Yeah.
Right? Do you have any expectation and something that can be easily achieved, or there are some issues to develop that industry?
Right now we also do the magnets for booster as well, which we need to run the energy. So we need to do with the laminated technique as well. We are working on it as well. The challenge, I would say, like normally the company in Thailand, they don't do any strange fabrication that they don't know. It's very good enough that we can find the company that would like to join the project and then to work together with us to build the prototype. And hopefully they can join later on to build the mass product, to have the mass production of all.
Thank you very much.
Okay, any more questions?
ข้างในไม่มีการถามใช่ไหมครับ
Or start other. Okay.
Yeah, yeah,
Okay.
yeah.
So you mentioned about the small lineup project for maybe sterilization or the food treatment or something. So it is based on the laboratory based or as an industrial based project. Which one? Laboratory.
Right now it's laboratory based.
I see.
She is the boss.
You were in charge.
The project for the big one, the new one,
Yeah.
is going to happen very soon. It's already started or?
I would say the construction will start within a few years from now.
So it means that in 9 or 10 years, we will have the new facility.
Yes, hopefully.
Yeah, it means that we need more people to fill up in this facility, both physicists, engineers.
You are right.
Yeah, so we could come to the academic side. Yeah, I mean, every organization in Thailand and also from Japan, yeah, we could help this facility to happen in Thailand. And it could open many opportunities for us to do research and
Yeah.
also industry and medical part. So it's time to come to the academic side. So if Professor Sakon can handle for building up all students or physicists to play in this role, yeah. And yeah, please welcome Professor Sakon Lim to talk about electron accelerator and infrared free electron laser facility for frontier science and applications. Please welcome Dr. Sakon.
Good afternoon, everyone. So my name is Sakon Rimjang. So actually study from undergrad and graduate level in Chiang Mai University. When I did my senior project in the last year of my bachelor degree, my project is the design of the solid green particle So just talk about the first one. So I did the design before I saw the real thing, and I just the first time I saw synchrotron source is everything still in the boxes. When I saw it, when I went there for some seminar after I did my bachelor degree. So it's glad to see that it's come to this day that they already have the real thing and they even have the new one in the future. So that is really good. So after I finished my bachelor degree, so I continue PhD. Not master degree, PhD, because it is a program in Chiang Mai University that if you get a grant that can support you both master degree and PhD, you can go directly to PhD level. And I took that grant. So my project is to design the first electronic gun in Thailand, and I believe it will be the first one in Southeast Asia as well. And also to design the Linux systems, to design the whole accelerator system, but based on the accelerator system at Stanford University. So I spent some time at Stanford University to study the real accelerator before I come back, and then with the team at Chiang Mai University, we built the first covalent terahertz radiation accelerator Linux in Thailand and also in Southeast Asia. And after I graduated, I went to do my postdoctoral research at DESI in Germany for 5.5 years before in that time I worked with the photo injector for the X-ray electron laser. And after that, I came back to Thailand and yeah, I don't know why I did that, but I came back and started a project that called infrared electron laser in Thailand, from X-ray to infrared. And yeah, this is what is a topic that I will talk about today. And before I go into the detail, I have to say that this is not only my work. Mostly it's based on the student and the collaboration team work that we work together in order to make this happen. Why we are interested in the infrared or terahertz radiation? I think for synchrotron light source, we saw that they focus mostly on X-ray because they would like to study down to atomic level. But for infrared or terahertz radiation, we would like to use it to study in the level of molecule. And this slide shows you that there are several. I have to say that there are 3 of the infrared regions that categorize according to the wavelength and also the application that we can use. So it's near infrared, mid infrared, and far infrared. So when I was PhD student, I never heard terahertz at all. In that time, my project called Generation of Far Infrared Radiation. But later, after I went to Germany, people start calling it terahertz. So now I even don't know where to separate between far infrared and terahertz. But since that the name of terahertz is more well known, especially in Thailand, we call terahertz technology. Therefore, we call our accelerator as terahertz radiation accelerator instead of far infrared accelerator. And you can see here that if you can build a machine that have both mid infrared and terahertz radiation, we can use it to study the vibrational mode of the molecule, including the linear vibrational in mid-infrared, and also the rotational vibration in far infrared or the terahertz region. And these vibrational of the molecule are very important in many material science or biology or chemistry. And how to produce the radiation? So actually to generate infrared is not difficult, but to have the good one is quite difficult because we would like to have a high brightness radiation. So if you can see here in the picture on the left that there are sources to produce the radiation. And when we would like to produce the radiation from visible light to X-ray, we can use synchrotron light source for that, or even mid-infrared radiation. But it's quite difficult to have one machine that can cover from terahertz to X-ray. So this day, for in the terahertz regime, for synchrotron light source, people don't do it. But I just have learned that in Germany, they even build the solid ring, the synchrotron, just to generate the terahertz radiation. So maybe in the future, I cannot use this light anymore. Because the synchrotron light source, we also cover the terahertz radiation as well, if they finish that project. Yeah, and another picture on the right side of the slide also show that the performance of the free electron laser compared to other type of the laser. And you can see from that picture that we can produce the free electron laser with high brightness compared to other or high output power compared to other radiation source at the room temperature. So this is very important because if you want to use other laser, you need to do it at low temperature. You have to cool down the source, and then you can get even not comparable power compared to the electron laser. So this is one of the reasons why electron laser is a good source for infrared, coherent infrared radiation. Okay, but people will have question, what is the electron laser? So the name laser is well known for the conventional laser, such that you know that the laser that we use in this day, even the pointer laser, it comes from the ground electron excitation. So we get like the bound electron laser. It happens when the electrons in the atoms or the molecule get energy. Then it excited to get higher energy state. Then it had to come back to the ground state because that is more stable for them. So then they emit the radiation in order to come back to the ground state. But for the electron laser, since we call free electron, that means it's not bound to anything, which is good. So yeah, it's not dependent on the atoms or the molecule. So but we use the X-ray electrons in order to produce free electron laser. There are many types of free electron laser. So the one that the first one and also well known in this day is the oscillator FEL. So this oscillator FEL use the same principle as the conventional laser, such that we have the optical cavity to help to amplify the laser power. But this technique is limited only up to the wavelength that not exceeds X-ray wavelength because it's very hard to find good optical cavity for X-ray. Therefore, they have other technique to generate X-ray electron laser. For example, the one that called SASE. So that is cell amplification spontaneous emission electron laser. So for its name, it means it uses radiation from electron itself to amplify the power or the brightness of the laser itself. And then there are also other techniques, for example, the laser shielded electron laser or the higher harmonic electron laser. But for us, at our facility, we will use the first one. And that is also another technique that I will talk about later. The advantage of the free electron laser compared to the conventional laser is we can change the wavelength of the laser easier than the conventional laser. How to do it? We can change the energy of the beam, or we can change the magnetic structure of magnetic amplitude of the underrator that we use to generate the laser. So this is one of the advantages is tunable frequency property. Okay, you already heard about the synchrotron light source. So I would like to compare the free electron laser and synchrotron light source. I have to say first, I don't say that it's better. So both of them are good because they are complement. They have something different. And if one facility have both synchrotron light source and free electron laser, that is the perfect case to work. And many labs have that synchrotron light source and free electron laser in the same size. So when you look on the right, on the left of my hand, on the left of my hand, there is a picture show the radiation source. So the first one is the bending magnet. We see that the intensity of the bending magnet is proportional to the number of electrons, and the radiation will come as spectrum. So you can choose the wavelength that you want to use by using a kind of monochromator to choose the wavelength. So it gets out very broad wavelength, but you can choose it by using monochromator. So the second one is using the Wiggler. The Wiggler is a kind of series of dipole. Make it simple, but it's not that simple. So it's a kind of series of dipole that when electrons travel inside the magnetic field of the Wiggler, it will oscillating with high magnetic field. So it's oscillating very fast and quite soft. So the radiation that we get from the Wiggler magnet will proportional to the number of electrons and the poles of this Wiggler. And the spectrum will have a series of narrow spectrum, but they are very close to each other. Therefore, the spectrum look like continuous spectrum, like as shown there. And another one is the undulator. So the undulator is similar to Wiggler, but have bigger magnetic field. Therefore, electrons travel inside the undulator with the trajectory change very small. So the radiation that we get from the undulator proportional to number of electron times number of electron square. So that three techniques are used in synchrotron light source depend on the property of the radiation that they would like to use. And these three techniques, I think the two techniques, the first one, if any synchrotron light source that have only the bending magnet, they will call it like a type of first generation or something like that. If they already have wiggler and undulator, they will get to be like the second or the third generation. But there is another one, the photon laser. This day is based on the linear accelerator, and we call it the fourth synchrotron light source. It's still synchrotron light source, but have higher intensity because it intensity proportional to the number of electrons square and the number of holes of the undulator square. And when you see that, you will get very narrow band of the radiation that you can adjust. Like I said, you can adjust either the energy of the beam or the magnetic field of the undulator. And when we compare the property of synchrotron and FVL, so for synchrotron light source, it is a circular ring, and you can have many beam lines which work in the same time. This is the advantage of the synchrotron light source. While for the FVL, you can have only a single or only a few beam lines that can work in the same time. For synchrotron light source, they have broadband or narrow band, depend on which radiation source that they use. If they use bending magnet, they will have broadband, or if they use undulator, they will have narrow band. But for FVL, we will get only the narrow band spectrum. Another one is a time structure. So Dr. Thomas already talked about the synchrotron also have two time structure, but I think the shortest one is in picosecond, but the typical one is in the nanosecond radiation pulse, while the photon laser will have shorter in femtosecond to picosecond pulse, radiation pulse. And when you compare at the same frequency, I have to say compare the same frequency. You cannot compare X-ray and infrared. So you have to compare X-ray synchrotron and X-ray photon laser. When you compare at the same frequency, you can see that the brightness of the photon laser will be about 10 to the 10 times higher than the synchrotron laser, because they are like they are packed in the beam are the electron are packed in very short distance. So when they radiate, they are covalently radiate. That's why the brightness is much higher than photon. So as I said, it's not compatible. It's not competition, but it's a kind of combinations of the property. They are just different. We cannot say this one is better than this one. They are just different. So, but we choose to use FVL because we have linear accelerator. And for the infrared regime, we don't need very high energy beam. So this picture shows the example of the infrared photon laser that operate this day. The first one finished in the Netherlands. This one have already many users. And they even have international user proposal that you can apply. So for Velvet in Dresden in Germany and also Friedhaber Institute in Germany, they also have their own user and also some external user. And although for Kyoto for university, so we are also one of their user as well, because we would like to try to use the FEL before we build our own, and also for other. So you can see that it's not big compared to synchrotron light source. It's in order of 10 meter, or maybe the largest is 20 meter, and the beam energy in order of a few mega electron volt compared to GeV. So this is fit very well to university environment, right? Because we don't have space, we don't have money, so then we just do something small, but also have good property. And that come to our project. So this is a map that I try to put all the facility I know on the map of the world. And you can see that there are several in Europe, also several in Japan and other areas. But in Southeast Asia, there is none. So that means with chance that we should be the first one to build this facility at Chiang Mai University. Why we do that? Because we already have the electron accelerator that can be used as a source of the free electron laser. We just have to modify the property of the accelerator. And yeah, because it's live, so I don't know, maybe we have some people from abroad attend the live. I would like to show where is Chiang Mai. So it's in the northern part of Thailand, and we are Chiang Mai University is the first university of Thailand outside Bangkok. I cannot say the best or not, but we are the first. The first is always good, even better. So we are the first university outside Bangkok. And our FBL facility is located in the facility that called plasma and beam physics facility, which we have three main research units. The first one is our lab working on electron accelerator. The second one is the ion beam accelerator, and the last one is plasma physics. And we are all called PBP or plasma and beam physics facility. This is the layout of our facility. You can see that it's not so big. I think in total it's around 20 meters, like 20 meters. But if you go there, no one will know that we are there because of opportunity. I'm sorry. Because we are most of our lab are underground or high behind some walls. So sometimes you just see a group of people come out from underground and they just come out. They don't know. People just wonder why we just come out because it's from outside. You don't know that there is our lab. So we have this accelerator underground, and we have up to 25 MeV electron linear accelerator and also beam line to generate the radiation, the electron beam. And we also have another area that we call experimental area. So at the experimental area, we plan to have both FEL and standalone station for user in the future using mid-infrared electron laser, terahertz electron laser, and other standalone station using hot power femtosecond laser. And this is the layout of the 3D model of our accelerator. So we have two beam lines for terahertz FEL and mid-infrared electron FEL. And we also plan to have the station to generate what we call terahertz transition radiation. Actually, the first part, I call it the state section. That is the one that we finished when I finished my PhD. And the extension is this one compressor, the turnaround magnet series, and also these two beam lines. This is a new project that we just did it like after we get some funding a few years ago. And we also plan to have another station to use the electron beam at the end of the space section. And this is the accelerator, how it looks like in our accelerator hall. So the picture looks nicer than the real thing. You can use Photoshop and so on. But if you go down, you don't expect to see that clean. And yeah, this is our accelerator. But the good thing is most of the components are designed and developed in Thailand in collaboration with several facilities, like both in Thailand and also abroad, also from Tomaku University. We got a lot of support from the group of Professor Hama. We also get support from Dr. Lau, who also here at the school, but he cannot come to see our lab yet because he still have duty to do at the school. And also some help from Stanford or SLAC facility. And we also from Kyoto University, from the group of Professor Oakil. And of course, we got a lot of help from Daisy, where I used to work before, and also from Narit and Singapore I saw. And you can see that all that part on the right side are what we developed here, mostly in Chiang Mai. And this is a plan why we would like to have this facility. we would like to have this facility in order not to use by ourselves, but to provide to other people, like to other researcher or industry. So we divide ourselves into two sides. The first side we call the accelerator-based experimental station, and another side we call standalone experimental station. Because for the user, only accelerator radiation is not enough. You need also other device as well. Therefore, we have two main activity in order to provide the service to the user in the fields of energy, quantum, material, biotechnology, and industry. And in order to do that, we also have the pilot application and the pilot group who come to help us to design and also to establish the station that fit well to their experiment. And on the right side is the benchtop or the standalone system that we have. And if someone want to use like our FAR spectrometer, also welcome. And yeah, okay, I don't have that one here because it's quite unique. And we will open it to service soon. But that means if you want to use it free, you can come now, but later it may not free anymore because we need some budget for the maintenance as well. So that's the first one. And you saw the third one, the terahertz time domain spectroscopy. So this system is developed by ourselves, but leading by one PhD student. So she designed, installed, and test this system by herself. And we can say that this is the first system that developed in Thailand. And it worked really well when we compare its performance with the commercial one. And now she is in Taiwan to learn even more technique to for the terahertz radiation. Okay. And for the accelerator base, so we also produce the terahertz transition radiation, which is good for two techniques, which is the terahertz imaging and the terahertz spectroscopy. So for the terahertz imaging, this is we get it from our radiation, but you can see the resolution is not so good. We still need to improve it, but that is in plan. And we also can do the terahertz spectrum using the terahertz radiation from the accelerator. Why I show this one? Because there are tons of applications for terahertz radiation. The first one is the terahertz imaging. I just get this picture from this website, and you see that we can use this in many types. And even yesterday we heard that Indonesia want to have the terahertz in the tank for security. So we can use it in industry, in defense and security, biomedical and other applications for terahertz imaging. And we also can use it for terahertz spectroscopy. And when you combine both of it, you combine terahertz imaging and terahertz spectroscopy, you get the signature of that material. And you can identify the property of the material, and you can use it, for example, like on the right side, that you can have spectrum in terahertz, which is not well known. So for MIR spectrum, we have already database. That after you get the spectrum, you know already what it is. But in terahertz region, you don't know yet because there is no complete database for that. So any spectrum that you get from your material is unique and new in the field. Okay. So now we come back to electron laser. So at our facility, we have two types of electron laser. The first one is the MAR oscillator FEL. So this one just shows the principle of the laser. We have the coupling cavity to couple the beam the radiation back to amplifier to modulate the electron beam and amplify the power. But another one we call the super radius FEL in terahertz region. But some people call it, sometimes they call it coherent undulator radiation. The name of coherent undulator radiation tells us that since it's radiate coherently, so then the power or the intensity of the radiation is proportional to number of electron square, which is very much because one bunch of electrons, you have like 10 to the 10 electrons in there. So therefore, the intensity for distillation is very high compared to, I think if you do the same thing with the oscillator FEL, the coherent underwater radiation, free electron laser has much higher radiation intensity or power. And why we would like to have that? Because there are advantages of the accelerator-based FEL. Like I already said that it's tunable, so we can adjust the wavelength. The power of the radiation is coherent, so it's laser, so it's coherent, and it has high brightness. And the last one, that is very special, it has very short pulse in the order of femtosecond and picosecond. So that means we can use it to study the dynamic that happen very fast, especially in the chemistry or biochemistry. And since it also has very high brightness, we also can use it in to study the low containment molecules. You may have like only a few molecules of something in something. But you want to study only that a few molecules. With this high brightness, you can use it. And we also can use it in the liquid state in quantum material at high magnetic field or study the chemical reaction and also for nonlinear response of the material as well. Okay, I should go faster. So how to use it? The first one, the easiest one is the high field aeration. So we already have planned to build the high field aeration following the concept from Kyoto University. And I just got that picture. I saw Dr. Monchai in the Zoom. So we try to take it with ChatGPT. This is a picture from ChatGPT. And yeah, with the aerations of MAR ultra-hertz FEL, we can not just characterize the property of the radiation, but we change the property of radiation. And we already did that. I saw that by my eye once we went to Kyoto University with the sample, the biochromium sample. We can see it from the white color to transparent color in very short time. So that means it changed. We don't know change in the good way or the bad way, but it's changed. And this is the example that quite well known in the field that they use the high field mid-infrared field electron laser to study what they call the amyloid fibrils. So which they have to form the beta sheet form and the alpha helix form. So this is the source of the disease that called neurodegenerative disease. So we can use it to study before it happens. So when how to do that? So from the right picture, it shows the spectrum of the of these beta sheets and alpha helix. So for some people said that why don't we just use like UV because it has higher energy? But if you use UV and not specific wavelength, you just change everything. But this one you shoot a specific wavelength. So for example, in this picture they show that the graph of the spectrum of non-irradiated and irradiated at different 3 wavelengths give different results. And this is the advantage of electron laser that you can choose its wavelength fit to the peak or because the peak of the spectrum tell you the molecular structure, right? So you can change exactly what you want to change. So this is one of the advantages of this high field aeration. And another one is the time resolved pump spectroscopy. So in some complex system and the change or the reaction happens really fast in the scale of femtosecond or picosecond. And as we know that if you would like to study something in short time, you have to have even shorter time to study, right? Therefore, electron laser is fit really well for this pump spectroscopy. So we can use it to study the change to pump the electron or the molecule into the excited state. Then we see what happened after that using also the electron laser as a whole. And this is the concept of what we call the pump of increment. And again, we have here the picture from ChatGPT. Yes, and there are two types of the pump of increment that we would like to conduct here. The one color from electron laser. One color means you pump with the same frequency, but before you pump, you may change the polarization or something. So we can use only electron laser, or we use it in combination with the laser from the femtosecond laser. And with that, we can have what we call the two-color pump of increment. This is very important because when we would like to excite the atom or the molecule, it needs higher energy than the pole the pole beam. So therefore, the two-color pump of increment is also another goal for us to develop in the future. And we also plan to have another station using electron beam directly, but not just like the electron beam radiation as usual. We would like to use this as a source to study the new concept of cancer therapy treatment, which very well known these days that we call radiotherapy. So when you have cancer cell in your body, it will be in between of the normal cell. So it's shown some result from experiment and some calculation that when we irradiate the cell that means between the normal cell and the cancer cell with very high dose, they can spare the normal cell better than the conventional irradiation. So that's why this spectral radiotherapy concept is the one that's quite well known and getting popular. And we have planned to do that in collaboration with the Peace Group at DAISY. Okay, and that from the accelerator. So I also talk about our benchtop on the standalone device. So we also have, I call it terahertz FTR spectroscopy because it has two light source in the regions of mid-infrared and also infrared or terahertz. But that's not as important as that we also would like to use it differently from the commercial one, such that we can couple it to another setup. For example, we already have the project with the National Astronomy Research Institution in Thailand to develop what we call the astrophotometry experiment in space. So they would like to study the origin of life in space. So therefore, they need to have the chamber that have a low temperature and also low pressure. And then they will shine the UV on the sample. And then we will use the FTR to study the shade during the time that they shine or they inject the UV on the sample. So this is also example that, but it's not only for chemistry. That sample, this sample also can use for other material like 2D material. We also have another researcher group that would like to use it with quantum dot because they also want to have the same condition, low pressure and low temperature by studying the shade. And yes, now I come to the homemade. We are proud to call it homemade because it's only developed in Thailand. Even the terahertz emitter and detector. So normally when the company they build the time domain spectroscopy, they will buy the PCA, which is used as a detector and emitter from other company. But for us, we use the one that developed by NECTEC, which also also in Thailand. We work very close together, and then we get that prototype. I cannot say prototype. We can have only one. I think we don't have enough money to have the second one. So that device on the right, that's working very well compared to the commercial one. And we even plan further that we will make it even more advanced, such that we will include also the dry air system and also the cryogenic cooler in order to support the user that want to have the condition according to their sample. And this is just the principle of the time domain spectroscopy. So you know FTR, you can get only the spectrum, but for the time domain spectroscopy, you also get the phase of the electricity. Therefore, you can study the compact property of the material. For example, the compact electric constant or the compact refractive index. So this is also good device to use. And we will provide it to users soon. So now we are in the state of the optimization of the system. And there are many applications that we can use terahertz time domain spectroscopy, especially in agriculture and food application, which fit very well in Thailand. So if you want to use it, you can come and discuss with us how to apply this device to your work. And also, it also can be used for nanotechnology application. And yeah, so I think actually I used a lot of time already. So it brings me to my conclusion, which I would like to put it as a picture. So this is the goal or the dream. I am not sure that it's our dream or only just my dream, but this is what we want to have for our facility, that you will have the device that provide for user that use radiation from both accelerator and also the one-top laser system and FTIR. And to do that is very difficult in the university environment. So therefore, we have to do a lot of things and also have to obtain some grant from outside the university. And because we are poor, but this is good point, because if you are poor, you will not use just money. You will work a lot in order to make it done. So we also can say that we are one of the university that can develop the manpower in accelerator, also laser, and also radiation, as well as the engineering aspect as well. So if anyone want to come and to become our researcher or our student, you are welcome. We have some grants, not much, but we have some grants to support. And you can apply the grant to university as well for good students. So I would like to stop with this one. There is a lot of more things that we have to do in order to complete what we want to have in the future. And yeah, we cannot come to this point without the help from the research team and the collaboration, and also the can support as shown in this slide. Thank you very much. Any questions? I saw, yes, please.
Yeah, I'd like to ask you your Swedish relation time.
You mean
What?
now?
Yeah, now. Yeah. How much day do you calculate? And what is the production for each experiment or treatment?
I have to say that actually now we for the accelerator based point of view, that one is still not in the operation, it's in the development stage. So we have planned that yeah, like I said, it is like more than 20 years old for the accelerator, but the power system has even longer history, 30 years old, and it sometimes it break down, so we have to fix them. So we try to fix that problem. So for that radiation from the accelerator, I think yeah, now we don't have provide to user yet, but we plan to do that in 2 years according to our funding that we submit to the government. But another part, the terahertz time domain spectroscopy and the FTIR, I think we for the FTIR we provide now mostly to the external user. So we also have some work that belong to our group, but I think the percentage of the user from outside the lab is more now. But for terahertz time domain spectroscopy, I think it's still in the state of the optimization. We have only a few. But as I promised to the funding agency, we should have at least 50 users per year in order to get new funding next year. So therefore, we have the assistant researcher just to help us to deal with the user for that. Yeah. Any more questions?
I'm also one of the users.
Yes.
Yeah.
And you can use it free now, but we will. No, she will be permanent free user. You run out of time.
Yeah, we ran out of time, but we still have question in the chat.
Okay.
Yeah. This question is from Professor Anusha that joined us in chat, but yeah, he left the question with me, then I post this question, and this question is for Professor Kuliti.
Oh, not for me. I'm sorry for that.
Yeah, according to your talk, yeah.
For ion implantation, in the calculator for my classification to put that in.
Okay, the focusing point of the ion beam strongly depends on the emittance and the optical system. So to make the very tiny spot size, we need a very high quality ion beam. That is one boundary condition. And yeah, once we had we realized that this condition that the propagation is very simple. And of course, in addition to that, we can control the depth of the implantation by changing the energy. Okay, that is the basic mechanism. So
Inflation, right? About the heat, about the this synthetic heat in the chip.
For the biological.
Yeah, for the.
I believe the energy itself of the cancer cell, for example, the particle cell and the X-ray and also the alpha emitter property, the energy itself is quite few. You know that means that the thermal energy is negligible, but you know that even the energy is quite few. The by radiation DNA will be damaged. So we utilize this nature.
Thank you very much, Professor Kuliki. And Professor Anusha, I think you already got all the answer, but for specific answer, you should stop by and talk to Dr. Kusadi. Okay. I think, yeah, because we have one ion implantation in our school. Yeah.
But actually, if he interested in the medical application, may come by for our school. Have one day of medical application.
And
He is also one of our team in material science.
yeah, I have one last question that professors are concerned. If we do the telehealth experiment now, we don't have any library to confirm the result. What we can do if we have some, like, if I have some reference sample and some the one that I modify.
Yeah, that's why we need also the computational team. Yeah, I saw at Philip when I was there for 2 weeks. So they have a big group of computational team together with the MBL team because for the even for mid-infrared radiation, you can do simulation, you can use DFT, you can use molecular dynamics to start to make a model of your sample. And then if you can simulate that spectrum heat, you will know what it is. So we have the team to do that also now, but not a very small team. Yeah. And we want to also include this into our plan in the future as well, that not only to do the experiment, we would like also to make a database of the thermal radiation. There are 2 ways. You just measure a lot, then you put it in database, and you can have a machine learning to measure sample to the spectrum that match, or you can do the simulation to specific spectrum.
Thank you very much. Okay, if no more question, I think it's time to close our public talk, and thank you all three speakers again. Okay, thank you very much.
Okay, actually, I would like to invite you so that